Hello. It's our pleasure to have with us Professor Deepa Venkatesh from Department of Electrical Engineering here at IIT Madras. She has been in the department for 7 years now.
7 years.
And before that, she was as a faculty for about 8 years in Mumbai.
Mumbai University.
Mumbai University. So that's where she's been for about 15 years as a faculty. That's a lot of experience as a faculty. And she has worked on photonics, nonlinear optics, fiber lasers, and optical signal processing. So a wide range of areas, and these are technologies that we often interact with for a lot of our communication processes. We're really glad that she could join us. So we will get an idea of aspects of research associated with electrical engineering. So Deepa, in electrical engineering, it's of course a field of engineering that has been around for a very long time.
Correct.
So are there areas of research that a PhD or an MS student might still encounter, which are considered traditional areas of research in electrical engineering, where there's a lot of literature available that they can refer to and has been around for maybe, I don't know, 10, 15, maybe much more than 20, 30 years, but still considered something that people have to work on, and there's a scope there to work on?
So thank you first of all for inviting Pratap. As far as electrical engineering is concerned, it's a highly interdisciplinary branch. So as you rightly pointed out, there is a lot of material available in Traditionally, electrical engineering was to do with power electronics, power systems, high voltage engineering, and electrical engineering or electronics engineering as it is called. Of course, in our department, it's all both together. It's machines, power, electronics, VLSI kind of work, and research is continuing in that area. So for instance, in today's context, you have a lot of solar things coming up, and you have local generation of power happening. So each consumer is now a producer of electricity also. So going from the power grid, which is a very traditional area, now you have inputs to take from those traditional areas, where earlier it used to be small hydroelectric projects which used to feed in power into the system. Now you would have smaller consumers sitting there and feeding. So I think a lot of inputs can come from that area. Similarly, VLSI, microelectronic, it's all a tradition which is already there. You start from there and then you start growing. Same for photonics. Photonics is an area which it's a counterpart of electronics, as we call it, right? Where things in electronics you control electrons, in photonics you control photons. So traditionally it is optics. Right? Okay. Traditionally you call that as optics, and then you start from the principles of optics, and then you see how it applies to an engineering perspective. So yes, there are different traditionally sensitive areas. If you take about, for example, communication, signal processing is one of the very profound or the very basic subject which gets applied in multiple different areas. It could be speech processing, it could be image processing, it could be processing for optical communication, it could be processing for wireless communication. So these are traditional areas. Definitely they do have a strong hold in electrical engineering as on today. But we'll see that things will change as far as research is concerned. Right? So in that sense, like physics or like chemistry, electrical engineering is not that you call it as a chaste subject where you keep following one specific area and you keep expanding on that. It's highly multidisciplinary.
Okay.
Right? So as somebody said, if you know mathematics well and if you know the physics of it, then you are pretty much well equipped to do electrical engineering. Okay. And where do you get those mathematics and physics? You got to get your basics right.
Yeah. Okay. Right. Great. So now, in the same token, so with various engineering disciplines, with the passage of time, generally new areas come up.
Sure.
And so in electrical engineering, is there something that's come up much more recently, let's say the last 5-10 years, that people focus on a lot?
Absolutely. One thing that you see, the solar we were talking about, right? So now how do you do this distributed grid? How do you do the smart grid? How do you do distributed generation? How do you feed it into the grid? That is in case of power electronics. So let me also tell you that in general, electrical engineering, we have 5 disciplines, major disciplines if you wish to classify. One is communications related area, which is to do with wireless communications. That involves a lot of hardware to make those antennas, to make the wireless systems, and more than hardware, a lot of software and mathematics. For example, if you are trying to send a signal from the transmitter to the receiver, the data rates are going up, so you need to model your channel very well. You need to do an adaptive control of your signal. You need to give a feedback adaptive. There's a lot of mathematics probability that goes in. So there is a large influx of highly efficient mathematics and signal processing going in that area. That is in the what we call as the electrical engineering 1 in our E1 in our IIT setup, but it's basically communication, signal processing and related areas. The second area is power systems and power electronics. So as I mentioned earlier, the distributed power scenario is one thing, power quality, power, when you have distributed system of every consumer starts feeding in power into the system. Now how does the electrical TNAB, for example, ensure the quality of power, right? Okay. So there is a software approach to that, there is hardware approach to that. So those are the advances in that area. Same way in renewable power, for example, wind, solar, how do you integrate it to the grid? Those are issues. And I think many of you might know the solar DC project, direct DC consumption, where how do you make your lights of course LEDs work on DC. How do you make your fans, your refrigeration, everything on DC, so that you can avoid the AC DC conversion loss. That's a very big project, and that's a highly socially relevant project also. So that's a lot of effort is going in that area. So that's to do with power systems, power electronics, machines. Another important thing in that area is different users will have different requirements. For instance, you're powering your satellite. The requirement could be small voltage but high current application, right? So how do you do those DC-DC conversions from you could be drawing the power from the grid, or you could be drawing power from solar, but one DC to another DC of different requirement, how do you do that? Even robotics, any area that you pick in of engineering, you would need that DC-DC converter. So that's another very important area, application specific DC-DC converter designs. Then the third major area of electrical engineering is microelectronics and VLSI. Microelectronics, I don't have to say that the granularity is going down. You are following Moore's law. You are going from nanometer to sub-nanometer kind of device dimensions. So you have all the associated maths and you have all the associated physics along with the fabrication technology for that. So you will have the other important area that has come up there is microelectronic and MEMS, what we call as micro electromechanical systems. Now that has evolved into nano electromechanical systems, where the device dimensions are very small and you will be able to control or switch certain devices. Plasmonics is another new area where metal interfaces can enhance certain properties of light, and so that is another area. Silicon photonics is another area where you can, just like how you had the electronic integrated circuits, you could have photonic integrated circuits where your motherboard. So the biggest problem today in a computer motherboard is how fast can you transfer from your CPU to your memory, right? Now if you can do everything in optics, where your transfer happens in optics, your processing happens in optics, that's the whole area of optical signal processing. You don't have to go into the electronic domain, and light being the fastest, you can do it at that speed, right? There's a lot of development happening around biomedical devices. How do you make simulators for making the surgery efficient, or giving practice to the doctors and things like that. So definitely yes, all these areas, so the control and instrumentation, and that's where we talked about biomedical engineering. Then of course we talked about photonics, where the other smart city scenario right now, people are talking about putting as many sensors as one can and then develop a sensor network. Again, it's completely interdisciplinary. You can't classify whether it's a photonics or a wireless communication, because all aspects of it is coming in there, right? So, so smart cities, you want to put multiple sensors. Now these multiple sensors, some of them could be electronic sensors, some of them could be photonic sensors. All of them should use a wireless communication link to relay the information to one central office. Then you would do the appropriate processes required. So yeah, so all these are coming up. organic electronics is another area where flexible electronics.
Okay.
Right. You would have seen advertisements from Samsung or somebody who would have made a TV which is flexible. You would have your cell phones which could be flexible. You can roll it and put it in your pocket. Question is, how efficiently will you be able to develop? How fast will these devices respond? Can I make a use and throw screen, for example, right? So it's completely evolving area, right?
Okay. So if we now look at, let's say, a student perspective of people coming in and so on. Of course, there is electrical engineering departments in almost every college, because it's one of the traditional areas of engineering. You have bachelor's degrees in electrical engineering being awarded by so many institutions around the country. When they come for a master's or a PhD program, are there still certain, are there certain challenges that they face? Of course, we are moving from a course-based work to a research-based work, so that itself provides some challenge. Correct. But other than that, specifically for electrical engineering, in terms of their preparation that you normally see amongst the student community that's coming in for a higher degree in electrical engineering, do you see that they face certain types of handicaps that they need to overcome, for which they are evolving certain mechanisms here, and if so, what?
So it's a very, very relevant thing that this is something that we keep discussing among our research group and the faculty group. And what we have always found is at the end of their undergraduate program, they are probably writing a GATE exam or some qualifying exam to get into our system. The examination systems are always checking your ability to remember certain things, or maybe at best in what we call as a Bloom's taxonomy of learning, at the base levels, where they learn something, they are able to reproduce something. They are at best able to apply a formula to a given situation. When they come into the research mold, they also need to research. The final goal in the Bloom's taxonomy is also in creation, right? So you would want them to be able to create something. Now, again, broadly classifying as in any other engineering or science streams, you could have theoretical work or experimental work. So let's talk about the challenges with the theoretical people who try to do simulations or theory. There, what we feel is the mathematics is not strong enough.
Okay.
Right? Their mathematics is not strong enough. As somebody said, if you get your mathematics, if you get your physics right, the rest is mathematics, is what somebody say. But that rest is mathematics is not very strong.
Yeah, it's very,
so yeah. They're able to. What we see is the students, if you give a stereotype problem, they're able to solve. But given a situation, they are not able to formulate a problem and solve. A part of the research training is towards that, I understand, but to correlate from different areas and apply in the same problem is something that we are finding, the students are finding it a bit difficult and challenging. Even in programming, people know how to write a C program with the same program with, or maybe a MATLAB code as they call these days. Use 100 lines to write something which is worth maybe 15 lines.
15 lines, okay.
So that's something that smart mathematical thinking is something that we would like the students to develop when they come in. And as far as experimental skills are concerned, partly because of not their problem, they are mostly not trained in handling equipments. And when I say trained, it means like we are not talking about the research level equipments. We are talking about simple things like oscilloscopes, right? Again, as I said, it's partly not due to their fault, but they even if they get a chance, lack of exposure. Most of the colleges probably run 4 or 5 people on one equipment. Some of them might be actually using it, some of them might not be using it. So my only advice to the student is, if they get a chance, they have to go and try and run experiments. And that experimental skill is something that it's not even experimental skill, that experimental sense is something that thinking on feet while running the experiment, those are the things I think our students find it big challenging. Third biggest challenge everyone faces is lack of ownership.
Okay.
Lack of ownership for a specific experiment that is done or a specific instrument. This microelectronics and photonics, most of the instruments are huge facilities, and I think it's more of a ethical culture than anything that can be trained. When you are working in a place, many of the students feel that it is like a college where I go in the morning, come in the evening, close down everything. My job is over. There's somebody to take care. But I think that has to change, and they should start getting. They should kind of find a unison with the equipment. only then the results will come out. Right?
Okay. Let's look at it from, say, the industry perspective. So, there is always this perception that when you do a master's degree, especially an MS or a PhD degree, research-based degree, that the student is becoming a specialist in a sort of a narrow field. And often MS PhD projects are also maybe a little ahead of their time in terms of because they are really pushing the boundary of some area.
Otherwise, you can't publish.
Yes. So, in that context, to what degree does the industry show interest in what MS PhD students traditionally do in electrical engineering? Are there areas that, even though they are advanced, the industry is now ready to absorb also at the same time?
Absolutely. I mean, electrical engineering, by the very nature of the projects that we do, is there are certain areas which industry might not be interested. Let me also say that, like, for example, quantum communication, for example, right, or a quantum computer, for example, is probably not something where an industry is
currently interested in.
Would not spend a lot of money on, right? But there are certain areas like that. But many areas that we are talking about, for example, this grid, right? I mean, it is an industry who wants the result out of this, right? Okay. So, definitely industry is looking forward towards many things that we are doing, especially in wireless systems. Some of the things that we do evolve as standards.
Okay.
Right, the kind of work that people do out here, they participate in standards. But as far as the student is concerned, I think PhD, once you get a PhD, I mean, when do you get a PhD? I think within a certain reasonable time, if you are able to absorb a new topic, let's say industry has a certain requirement, somebody who has a PhD should be able to understand, absorb that topic and provide a solution given a reasonable amount of time. It need not be directly related to what they have actually done.
Okay.
So, in that sense, when they graduate with a PhD, it's probably not necessary that it is directly related to what
their area of specialization
is.
So yeah, in that context, in fact, I mean, taking that forward, what sort of positions do you see MS and PhD students in electrical engineering normally picking
Most of the students go for, the MS students go for PhD and PhD students go for postdoc. But having said that, there are many students who are absorbed in the industry also. They do core job. For example, we have from our photonics group, one of our students have gone into, in fact, my student went into an industry. Just after PhD, he was absorbed in Tejas Networks, which is a pure communication company. Whereas his project was on optical signal processing. It has probably 10 years into, I mean, I cannot think of an optical signal processor which he had implemented in his PhD getting implemented in the industry for next 10 years. I can't see that happening. But the kind of expertise that you develop during that, he got placed in Tejas Networks. There's another student who got placed in GE, for example. I mean, there are certain core areas. Again, these are not related directly to their PhD problem per se. There are of course also cases where after their masters or PhD, they have their own startups. People have started, for example, solar electronics, I mean organic electronics. There are a couple of group of students who have had their startups coming up. So, there are different possibilities one can think of.
Yeah. A couple of things from let's say a faculty's view of what's happening with respect to a student. At least during their student life as a research scholar, as a MS or a PhD student, and maybe even in their early career after that, how are there ways in which you measure success in research, other than I mean, traditionally people talk about publications.
Correct.
But that is certainly something we will still continue to look at. But is there any other way in which you look at students and feel that in fact this student is growing as a researcher compared to somebody else that you see?
Absolutely. I think that goes without saying. Every research guide, when do you again get your student ready for graduation, and the student is able to give you ideas which the guide has not thought about. Student is independently proving certain things, is coming up with multiple ways of solving the problem. I think that is how you measure success.
Okay.
And the way to quantify that is of course your patents, your papers, the number of citations you have had. Citation is of course something that comes up over years, but the measure, I think the immediate measure, which is probably not very quantifiable, is coming through discussion between a faculty and a student, is when the student is trying to think of or giving us new ideas rather than we giving them the ideas. I think that's a measure of success.
In fact, on a more mundane note, we always say that students have, I mean, at least especially as a research scholar, interaction is a very important thing. How well they interact with other people in the group, how well and how often they interact with the guide. In your view, how often should students be meeting their guide, advisor?
So there are two things. You pointed out two things: interaction with the peer group and interaction with the guide. What we have set up in the Photonics group is, of course, changes from guide to guide, but at least we say once in a week is the minimum number. Meeting more often than that would mean that the student is dependent on the guide. Okay. And meeting less often, probably the student will go out of track. So we believe once in a week is something. But what we stress on more importantly is their peer interaction. And one of the things that forces the peer interaction is, it's a fairly big group. There are about 6 of us who are working together if it's a research group like that, if people can afford to have that kind of setup. The best thing is to have them organize peer seminars. It could be on a small topic where faculty is not typically invited for that. It could be discussion of a research paper where peer learning is much more valuable, we feel, especially in certain areas which are highly interdisciplinary. Right? So I think it's important that the students talk to each other, give presentations to each other, get inputs from the seniors. Then of course the guide, meeting with the guide at least once a week is what I would say. And I would also say that the students have to attend other talks, right? Other talks from related area. It could be in a different department altogether, but if it is having some connection to their research work, it is, even if it's not a connection, it's good to attend those talks too. I mean, that's how they learn, and that's how they kind of apply what others are doing to their own work, right? So they should have that bigger vision, or bigger view for eye for those things. Right? Yeah.
Okay. So, I would say, sort of to conclude, what are your words of advice to any student who is aspiring to join an MS or a PhD program in electrical engineering?
So we have covered that mostly. One is their mathematics they need to work on, right? Whichever area in electrical engineering you want to work on, if it's something to do with VLSI, or I mean, it's your physics and mathematics basically. So we work on your physics and mathematics. Then also have this idea that research is not a time-bound program, right? The advisor does not have a solution. If the advisor has a solution to the problem, he doesn't need a student. The advisor can work towards that problem. So don't expect a final answer from an advisor. It is probably the goal is also not very clear. Only the problem is clear, right? So that will evolve. So need to have that patience and that kind of temperament, that inquisitiveness to go further. Again, talk to other students and try to understand what their problems are, how have they solved those kind of problems. Teaching helps, so try and be a proactive teaching assistant if possible, because when you try to teach certain things, you will get the connect and some of your research problems get solved. There's no documentary evidence for that, but I feel that teaching helps research and research helps teaching. So given a chance, try and teach certain things when you are in the program, and get your maths and physics right.
Okay, great. On that note, thank you so much for joining us. It was a pleasure to have us.
Yeah, thank you.